Good afternoon
Good
from the
afternoon.
UK. Yeah, my name is Florence. I'm here to make a presentation entitled Characterization and Hydrodynamic Evaluation of the Relationship between Permeability, Microstructure Parameters of Ceramic Membrane for the separation of oil-water emulsions. I'm going to make this as brief as possible because I can look at that we are out of time. So we have our outline here, which inculcates the introduction, the overview, aim, methodology, and the like. So oil water emulsions are then generated daily from different industrial activities, and it needs to be treated before it's disposed into the environment. And the proposed method I'm using for that treatment is, sorry, I forgot to put on my video. I need you to see my face. Okay. So, the proposed method is ceramic membrane, and it has been chosen for its desirable features, which is mentioned later in the slides. And these ceramic membranes are to be characterized, and the microstructure of the ceramic membrane are to be measured, because we feel that there's a relationship between the microstructure and the flux of water that can be separated using ceramic membranes. So looking at the aim of this work is to analyze the relationship between characterization and microstructure of ceramic membrane in gas transport and pure water. So this is what the ceramic membrane looks like, and this is actually a commercialized ceramic membrane. The desirable properties, it has a longer shelf life, self-cleaning properties, mechanical thermal strength, and can survive in organic solvents. And if you use it, it has the elimination of secondary separation. These are the characteristic features of this particular ceramic membrane. Looking at the length, the outer diameter, the inner diameter has all been measured. So basically, this is a schematic diagram of my rig setup, and it's consisting of a feed tank which houses the oil water separation and the oil water emulsion. There's a peristaltic pump that pumps it into the membrane module C, and the membrane module houses that membrane, the ceramic membrane that has been used, and there is a pressure gauge to measure the pressure that goes into the membrane module. Basically, the water passes through the pump, through the membrane module, and is separates oil from water, and comes out into the cylindrical, on the weighing balance, into the measuring cylinder rather. And whatever that is not separated with the membrane passes out through the retentate E through a flow meter and back into the feed tank. So it's a continuous process. So because we are looking at the hydrodynamic nature of this ceramic membrane, we had to use gas transport rig to measure water flux using gas transport rig to measure water flux that has been experimented in the lab. And this is actually made up of the gas, ceramic membrane module, flow meter, and indeed, whatever gas that passes through the membrane module escapes back into the fume cupboard. So that's the schematic diagram of it. The Carman, Kozeny, and Hagen equations were used to analyze the porosity and tortuosity of the ceramic membrane, because these are the microstructures that influences the flux of the ceramic membrane. So the characteristics or components of each of those equations are listed below. So we were able to use from literature figures to obtain porosity. And from porosity, we use this equation to calculate tortuosity. This is the literature that I'm talking about. We used it from, we inserted porosity that was generated from the lab to calculate tortuosity. Aside that, we also used the Hagen-Poiseuille equation to calculate tortuosity to confirm the accuracy of the tortuosity. There was a characterization done using scanning electron microscope to determine the pore size of the ceramic membrane. We also looked at ISAC to determine the elemental composition, because this work is basically about characterization. It is clear that the flux of the gas are on this table, and 3 different gases were used: nitrogen, argon, and carbon dioxide. We were able to run using the rig setup that I showed previously, pure water flux, and this was the out volume as well as the flux. It was done a repeated times 5, and with average was gotten below. The results indicated that from the gas transport, pure water could be deduced using the intercept on the vertical axis. And we look at the intercept on the vertical axis. It was an average of 0.05. And we looked at the pure water. From the table above, the pure water flux average was 0.05, which means that gas transport can be used to deduce flux as well. So we discovered eventually that an uneven spore size was then depacked for the SME result, and then that the intercept of gas flux from linear equation is 0.592 rather. This corresponds with the experimental water flux, which is 0.0578. The porosity was measured using Archimedes' principle to be 0.04. Furthermore, the Hagen-Poiseuille equation was also used to obtain estimate for tortuosity, which was close to 1. So using literature, tortuosity was 3.77, while using the structural data from the lab, tortuosity was 1. This discrepancy is due to pore size distribution in the membrane, which ranges from 12,000 nanometer to 50 nanometer. So in conclusion, from the experiments carried out, it can be confirmed that the absolute pure water flux measured corresponds with the value obtained from gas transport measurement. It can also be confirmed that tortuosity measurement from the Hagen-Poiseuille equation and literature fall within the range of 1 to 3.77. The larger the porosity, the smaller the tortuosity, and the higher the flux. That was what we were able to deduce. So the next step for this research is to undertake some microstructural characterization on coated membrane using nanoparticles. These are my references, and I thank you for listening. If there's any question, please, I'm here to answer.